All right. My encoder says I'm live. Let's see when YouTube and Twitch agree. Good morning, everybody, when you finally hear this. Looks like Twitch is go, and now we're just waiting for YouTube. There we go. Excellent. Hello. It is pretty cold in Seattle today, so if you hear fans going off in the background, it's going to be my heater kicking on, and I'm not turning it off because it is very chilly. So I'm going to apologize in advance if that happens. But let's distract ourselves by getting back into BERT. So we are in the third part of the series now. I think this might be the last week that we spend on this. We'll see. And so far we did sections 1 and 2, and we're going to jump into 1, 2, and 3 because we are on the experiments now, I believe. Let's do a quick recap of what we've done so far, because last week I wasn't working on this. I did the pipelines live streaming instead. So BERT is a variation on the transformer architecture proposed in Attention is All You Need. I should note again that this paper has not been published, so it hasn't undergone peer review. I mean, people in the field have read it, but it hasn't been accepted by a publication venue, so just keep that in mind. And the bidirectional is similar to bidirectional LSTM in that we are looking both behind and in front of the current token. The encoder part is because the original architecture was for string transduction, or sequence to sequence. So it had an encoder and a decoder, and we are only looking at this first half here, this encoder. And this is from the Attention is All You Need paper, which we read previously. The representations are because this is a language model, I believe. Let's actually see where they get that from. The bidirectional representations, jointly conditioning, BERT representations. Yeah, so I think the representations is just to let you know that it's a language model, which is a mathematical way of summarizing the most likely ordering of words in a language. Anarchy says, hey. Hey, Anarchy. And then transformers is the specific architecture that they're using. So, Yash Middle says, can you quickly help us understand what is BERT, ULM, fit, and transformer? I don't think we've talked about ULM fit yet, but I can quickly talk about transformers. So transformers are a relatively new type of neural network architecture. So you may be familiar with recurrent neural networks, which have sort of a structure that has it can be recursion, but it has sort of like a circular structure, and then you take that structure and unroll it. So I look at X and then do, additional transformations and then come back to X again, except when I'm looking at it over time, X becomes the thing at the first time point, and then second time point, and then third time point, and then fourth time point. So that was not maybe the best unrolled RNN. Maybe not the best explanation because I was using my my hands. So we have this sort of circular structure here, and then when we are looking at a sequence, we apply that same structure to every item in the sequence, including as input information from the previous item in the sequence. So the big drawback of recurrent neural networks is that you need to have done X sub 0 in order to get to the point where you can look at X sub 1. So that's a bottleneck in training and inference. So they can be a little bit slower to train. Convolutional neural networks are more commonly used in Computer vision. Nope. Thanks. That is not what I was looking for. Our way of representing a two-dimensional space as a set of smaller representations that summarize the information in the two-dimensional space. And because there's no sort of ordering, like pixel 1, 1 is not in some sense bigger than pixel 1, 2, you can parallelize these a little bit better. And they have been used some in NLP, natural language processing, but mostly for most things, bidirectional LSTM with attention, which is a type of recurrent neural network, tends to be the dominant architecture. And then we have this new architecture called a transformer, which is there like a really good image in here? I don't think so. Has similarities to both. But the big thing is that at each time point, you look at at each stage of training, you look at every item in the sequence, and the relationship between items in the sequence is represented by different attentional weights. So that's sort of the difference. Some people also call transformers fully attentive networks. So instead of just attending to previous items, you attend to everything in the sequence. And because you look at everything at once, you can parallelize them a little bit better. So they can train a little bit faster. One of the big drawbacks of transformers, however, is that they don't seem to be as good at capturing hierarchical relationships. So things like, let's say sentential negation. So if I say, I'm trying to come up with a good example. So I could say something like, I did not eat olives and ice cream, whether or so in that sentence, the not would apply to both the olives and the ice cream. So it's negating both things. It has a hierarchical position above them in some sense. Whereas if I said something like, I didn't eat, the not is transforming, has a stronger effect on the verb eat rather than the sort of like things that come after it. If that makes sense, because there's nothing after it. Anyway, transformers are potentially less good at capturing information about hierarchical structures, which are extremely important in language. So, some benefits and drawbacks. The answer to life says RNN suck. They have been the bane of my life with all the gradient issues. They're tricky. They are tricky for sure. Although if you've been watching my live coding, you know that I just trained a transformer that has no output. So transformers are, I think that one is probably user error rather than having something weird in the gradient space. But I guess we'll find out once I fix it. So that's a sort of general idea of the architecture, except sort of the thing that came up at the end of the time last time. Oh, and here's a little visual representation. So a transformer looks at things at the current time point and also things after that time point and before that time point. And an LSTM looks at things in order and sequentially. The thing that we figured out last week is that it's possible that the biggest contribution of this paper is not actually the architecture, but actually the sort of masking training task that they're using, which I believe they claim is novel. And I do not know denoising, predict the mask words. Yeah, so it is the masked training process that seems to be the most important contribution, potentially, rather than their network architecture. I guess we'll talk about that when we get to the results. Bim ready? I'm probably saying that incorrectly. My apologies if that is so. Asks, how is Transformer different than RNN in terms of performance? That's a great question. We'll get to that today when we talk about the results section of the paper. And the thing that they are predicting with this language model is they have input sentences, and they are removing some of the words in the input sentences, and the model is being asked to predict them. The answer to life says transformers are much faster. They are much faster to train. That doesn't necessarily... Yeah, they're not necessarily going to perform better in terms of the task at hand. So transformers have had a lot of success in machine translation specifically. This is sort of, this paper is saying that, hey, we can also use them for language modeling. For most tasks that I know of at this point, even though transformers have had success in some tasks, they are not able to, or they currently aren't outperforming flavors of RNNs in terms of accuracy, or whatever metric it is that you are chasing. It's an evolving field. So that's where we were. We talked about the network architecture. We talked about the task in depth the last two times. And now we're going to look at the empirical results. Metalinx says, hi, everyone. Hi, Metalinx. On Twitch. Okay, so starting with section 4, experiments. In this section, we present BERT fine-tuning results on 11 NLP tasks. 4.1, glue datasets. The General Language Understanding Evaluation, GLUE benchmark, Wong et al. 2018, is a collection of diverse natural language understanding tasks. Most of the GLUE datasets have already existed for a number of years, but the purpose of GLUE is to 1. Distribute these datasets with canonical train, dev, and test splits, and 2. Set up an evaluation server to mitigate issues with evaluation inconsistencies and test set overfitting. Okay, so this is sort of, if you do Kaggle competitions, a little bit similar. They are, the people who are running the task are actually the ones who are running the evaluations and who are doing the specific train development and test set split. Oh, what's that? Sorry about that. Sneezy. Glued is, some emergency mutes there. GLUE does not distribute labels for the test set, and users must upload their predictions to the GLUE server for evaluation with limits on the number of submissions. Okay, so very similar to a Kaggle competition, if you're familiar with that. The GLUE benchmark includes the following datasets, the descriptions of which were originally summarized in Wong et al. 2018. MNLI, multi-genre natural language inference, is a large-scale, crowdsourced entailment classification task. Given a pair of sentences, the goal is to predict whether the second sentence is an entailment, contradiction, or neutral with respect to the first one. The answer to life says, bless you. Thank you. I think I've actually looked at this previously. Do we have examples here? We don't. Let's actually head over to the GLUE dataset and see if they have nice little examples of what all these things are. Because I think most people who don't have an NLP or linguistics background aren't super... Oh, look, they got a leaderboard. Aren't super used to some of these terms. So we can see that human baseline right now is the highest performing. Big Bird, which I'm not super familiar with, is the second high performing. BERT, which is the paper that we're reading right now, is the third highest performing. Transformer, I'm assuming the GPT here also stands for transformer. I don't know what the MT stands for. Probably some sort of transformer. Blah, 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 blah. Tell me your... Okay, nope. The little link URL... Here we go. Multitask deep neural networks for natural language understanding, cross-task data. Sorry, so I'm reading about the current leaderboard. Here's new, state-of-the-art, demonstrate, domain adaptation, in-domain layers, then BERT representations. Our code and pre-trained models will be made publicly available. All right, that tells me nothing about your architecture. But they didn't say transformers. So it looks like the current leader is not transformers, and then we've got 3 transformers, and then some BIOSTM with attention. And you can see that there's a lot of bidirectional LSTMs here, looking at the different approaches that have been tried. So anyway, I was looking for more information on the specific tasks, and I was looking at the way of multi-genre natural language inference. I was looking for examples of the entailment, contradiction, and neutral sentences. Do you have a nice project web page with examples? Yes. So we have some examples here. So the sentence is, the old one always comforted Kadan except today. And the hypothesis is Kadan knew the old one very well. So this sentence doesn't entail this sentence. So there's no logical entailment relationship between them. Rohit says, hey, what kind of prerequisite knowledge do I need to follow along with this paper reading? That's a good question. I guess ask questions if you're not getting something, and we can take some time to dig into that. Yeah, I mean, I want it to be accessible to everyone, and if folks aren't like, I have a question, I will just assume everyone is following along well. So please jump in. Yeah, I'm happy to meet y'all where you're at. Okay, so more examples. So the hypothesis is hundreds of students will benefit from your generosity. The sentence, your gift is appreciated by each and every student who will benefit from your generosity. These don't entail each other. An example of something that does entail something, at the other end of Pennsylvania Avenue, people began to line up for a White House tour, does entail that people formed a line at the end of Pennsylvania Avenue. So this is sort of a general statement that is true if this statement is true. So sort of the classical example of logical entailment for semantics is if I have 5 dogs, it is also true that I have 3 dogs and that I have 2 dogs. And that I have 1 dog. So the sort of more general statement is true given a more specific statement. And then an example of contradiction would be like, yes, now, you know, if everybody, like in August when everybody's on vacation or something, we can dress a little more casual, or and then it contradicts that August is a blackout month for vacations in the company. So we say here, August, everybody's in vacation, is in the target sentence, and then the hypothesis is that no one is on vacation in August, and we can tell that that's not true given the sentence. So it contradicts the sentence. So it looks like it's a 3-way classification task. QQP, Quora question pairs, is a binary classification task where the goal is to determine if 2 questions asked on Quora are semantically equivalent. I'm gonna go with we probably don't need to go into this one too deeply because there is a whole Kaggle competition around it, and the forums there are a very rich source of information. Scrolling down, I just want to go through all the tasks and then we'll pop back up and read all of these charts. QNLI, Question Natural Language Inference, is a version of the Stanford question answering dataset, which has been converted into a binary classification example. The positive examples are question sentence pairs, which do contain the correct answer, and the negative examples are question sentence from the same paragraph, which do not contain the answer. Okay, so that seems pretty straightforward from the discussion. At least to me. Again, please jump in with questions. I am very happy to slow down or go faster or go off on tangents. Okay, and then the answer to life says, lol, I love how half the paper so far has been nothing about BERT, but just about random NLP benchmarks. I mean, tasks are important, right? I'm definitely a person who came into data science because I really cared about the data. So this is the part of the paper that, for me at least, is the most interesting. SST2, the Stanford Sentiment Tree Bank, is a binary single-sentence classification task consisting of sentences extracted from movie reviews with human annotations of their sentiment. So is this review positive, negative? I don't know what all the annotations are. COLA, C-O-L-A, the corpus of linguistic acceptability, is a binary single-sentence classification task where the goal is to predict whether an English sentence is linguistically acceptable or not. Do they mean that in like the linguist way where we try to violate islands, or do they mean that in sort of like gross language policing way where they're like, hey, you're not good enough at English? Probably the former. Let's see. Oh, they set up some Kaggle competitions, so y'all could play with that if you wanted. Examples. Yeah, okay, so it is in the linguist way. So some good sentences would be, the book was written by John, she voted for herself, I saw that gas can explode. So these are sentences that an English speaker might produce and that make sense. And some bad sentences are, in which way is Sandy very anxious to see if the students will be able to solve the homework problem? So I think that's an island violation. And then another unacceptable sentence is books were sent to each other by the students. I think that's also an island violation. Oh, no, that's not an island. That's not an island because there's not a WH word in it. Sorry, I am digging deep into my my syntax. Very rusty syntax. It's a co-reference problem. Anyway, it's a sentence that a human probably wouldn't say and is a little bit hard to interpret because the syntactic structure does not accurately capture the intended semantic meaning, more or less. Okay. How do they get the bad sentences is my question. Oh, they got the bad sentences from linguistics publications. So these are made up by linguists as examples of things that don't work. Okay, that makes sense. That's a cool corpus. I wasn't familiar with that. And then STSB, the Semantics Textual Similarity Benchmark, is a collection of sentence pairs drawn from news headlines and other sources. They were annotated with a score from 1 to 5, denoting how similar the two sentences are in terms of semantic meaning. Okay, so this is given two sentences. Are they super similar? Are they super dissimilar? MRPC, Microsoft Research Paraphrase Corpus, consists of sentence pairs automatically extracted from online news sources with human annotations for whether the sentences in the pair are semantically equivalent. So sort of similar. Is it a very similar sentence to each other? Okay, no, this is binary and this is multi-class. Not multi-class, so this is a scalar judgment, and this is a binary, are they similar or not? RTE, recognizing textual entailment, is a binary entailment task similar to MNLI, but with much less training data. So we talked about entailment a little bit. And WNLI, Winograd NLI, is a small natural language inference dataset deriving from Levesque et al. 2011. The GLUE paper notes that there are issues with the construction of this dataset, and every trained system that's been submitted to GLUE has performed worse than 65.1 baseline accuracy of predicting the majority class. We therefore exclude this set out of fairness to API GPT. For our GLUE submission, we always predicted the majority class. Sorry, there's a garbage truck outside, and I don't know if you can hear it, but it's very clunky. So let's look at the sort of things that they did. Actually, let's read about them first, and then presumably they're going to send us up to so then they're going to send us up to those figures. GLUE results. To fine-tune on GLUE, we represent the input sequence or sequence pair as described in section 3, which we talked about last time, and use the final hidden vector, weird-looking E guy, R with spaces in the middle, raised to the power of italic capital H. If someone wants to tell me what the math words are to say that, please feel free. Corresponding to the first input token as the aggregate representation. So the way that they are doing their tasks is that they are tokenizing their sentences, and then at the beginning of every input, they are adding a token that is the label for that particular sentence. So if we were looking at the example of STSB, the first token would be a label between, not similar at all and very similar from 1 to 5. And then the final vector representation for that particular slot in the sentence would be the thing that they are using. Oh my god, they're so loud. And I am Sharkskin on Twitch says C is a real vector with H dimensions. And then the Answer to Life on YouTube says C is a member of the real number set in H dimensions. That's helpful. Thank you. So H being the dimension of the hidden vectors, which is going to be the same for every token in the input. And they're all real numbers. Thank you, helpful. Sajay says, hi. Hi, welcome. This is demonstrated visually in figure 3A and B. Are you going to talk about the other figures in 3 anytime? Maybe not. Okay. The only new parameters introduced during fine-tuning is a classification layer, W, which is a member, which is a vector, no, which is a matrix of k by h dimensions, and they're all real numbers, where k is the number of labels. We compute a standard classification loss with C and W, i.e. log of softmax, U of W times to the t. So let's go back up and look at this table that they pointed us towards earlier. So we have this, oh, that's right. So when they are doing things with pairs, they add both sentences together and have this sort of like first token that's a label token. And then they have a specific separation token. And then they have an encoding layer, the segment embeddings layer, which is the position, which for each token indicates the membership of that token to a specific segment. And then they are also using position embeddings that are learned rather than the sinusoidal position embeddings that we talked about previously in the Attention is All You Need paper. And if you were there for that reading, that was the part of the paper I was most confused why they did that with. It seemed like they just wanted to do some fancy math, and then they did some fancy math. Which is fine, but not necessarily, I'm not necessarily a fan of fancy math for fancy math's sake. Okay, so this is for sentence pairs. For single sentences, they just tokenize the sentence. The sequence layer is not included. So I think here for the embeddings, the prime here means that it's from the second sequence, and this one just doesn't have that. For question answering, the okay. So these are all giving out a single class label. So we start with the what's this called? We start with this this token that is a label of the rest of the sequence, and then we take the final vector after training from that specific token, and then that's what we label. And we haven't yet talked about the output of the question answering tasks or the single sentence tagging tasks. I think we'll get to that a little bit later on. The Answer to Life says sinusoidal position embeddings are mathematical banter. Ryan says sinusoidal position embeddings are job security. And Jan says, greeting to the group, my favorite data scientist, Dr. Tapman. Sorry I'm a bit late. Oh, welcome. That is okay. These are recorded. Yeah, okay, so I'm good with, this is making sense to me, the top half of this and how they're doing classification. And we haven't quite talked about this part yet, although question answering is almost, question answering, I would say, is more of a sequence to sequence task. So I am that's not something that I would just use an encoder for. I'd probably want a decoder as well. So I'm interested to see why they have chosen this particular architecture, which I'm sure they'll talk about when we get to that. And then this single sentence tagging tasks, NER, named entity recognition. So this looks like it's putting out, we haven't gotten here yet, but it looks like it's giving out a single label for every token in the input, with whether or not it is a named entity, I guess, more or less. We'll get to there. Let's see. Our task, so this is the label, the caption for the figure. Our task-specific models are formed by incorporating BERT with one additional output layer, so a minimal number of parameters need to be learned from scratch. So BERT is going to be the same throughout across all of these tasks. Among the tasks, A and B are sequence-level tasks, while C and D are token-level tasks. In the figure, E, here we are, represents the input embedding. T sub I represents the contextual representation of token I. So this is sort of the output of the model. CLS is the special symbol for classification output, and SEP is the special symbol to separate non-consecutive token sequences, which we've talked about previously. So that's the classification tasks. We use a batch size. So going back to section 4.1.1, we use a batch size of 32 and 3 epochs, or epochs, over the data for all glue tasks. For each task, we ran fine-tunings with learning rates of phi e to the negative 5, 4 e to the negative 5, 3 e to the negative 5, and 2 e to the negative 5, and selected the one that performed best on the dev set. Additionally, for BERT large, we found that fine-tuning was sometimes unstable on small datasets, i.e., some runs would produce degenerate results. So we ran several random restarts and selected the model that performed best on the dev set. Interesting. With random restarts, we use the same pre-trained checkpoint but perform different fine-tuning data shuffling and classifier layer initialization. Interesting. So sometimes, on some small data set, it just collapses completely, and they don't talk about why. Maybe they'll talk about it a little bit more in the future? Shed says, but isn't the textual output like a decoder? We're responding to when I was talking about how for question answering I'd want a decoder probably. Yeah, it is like a decoder. I don't know, I feel like you'd probably get better performance if you did a full encoder-decoder architecture, but you don't need a decoder for the sentence level classification tasks, so maybe that's their reason for not doing it. Sometimes it just don't. For BERT large, sometimes we found that fine-tuning was unstable on small data sets. So we just fluffed around and tried a bunch of different stuff until we found one that worked. Just for BERT large, the small one didn't have this problem. And there is also a footnote from, when we were looking at the recognizing textual entailment point, note that we only report single task fine-tuning results in this paper. Multitask fine-tuning approaches, I'm assuming, could potentially push the results even further. For example, we did observe substantial improvements on RTE from multitask training with MNLI. The answer to life says, wait, I never understood what the difference between the dev/valid set and test set is. So the dev set is the set that you are given that contains the labels. So it's the big data set that you are given. And glue, let's see, when they talked about it a little bit. So the training set is the data you're supposed to use to train on. The dev set is the data that you have the class labels for that you're supposed to use to test on. And then the test data is the one that you don't see. So like the Validation data is generally how I've seen those terms used. We use slightly different terms on Kaggle, which is super confusing. Yeah, hopefully that helps. This is so, sorry, this is just like, anyway, moving on. We note that the glue dataset distribution does not include the test labels, and we only made a single glue evaluation server submission for each BERT base and BERT large. Okay. Results are presented in Table 1. Both BERT base and BERT large outperform all existing systems on all tasks by a substantial margin, obtaining 4.4% and 6.7% respective average increase improvement over the state of the art. Note that BERT base and OpenAI GPT are nearly identical in terms of model architecture outside of the attention masking. So like I mentioned last week and earlier this week as well, the actual like contribution of this paper is the masking task. For the largest and most widely reported glue task, MNLI, BERT obtains a 4.7% absolute accuracy improvement over the state of the art. On the official glue leaderboard, BERT large obtains a score of 80.4 compared to the top leaderboard system, OpenAI GPT, which obtains 72.8 as of the date of writing. And as we saw looking at the benchmark, this is no longer the case. Right now, Microsoft has the top spot. Danielle says cross-validation. Yeah, I don't think they're doing cross-validation. I think they're using the whole training set to fine-tune their existing model. Anyway, this paragraph is just like, yeah, we did better than everybody else, which is a paragraph you will find in most published machine learning papers because that's the way that we evaluate systems right now. And yeah, they've just sort of bolded it. It's bigger. Our numbers are good. Why does only BERT large blow up and only sometimes? Sorry, this makes me feel uncomfortable as a scientist. The number glue test results scored by the glue evaluation server, the number below each task denotes the number of training examples. The average column is slightly different than the official glue score since we exclude the problematic WNLI test set. OpenAI GPT, BERT base, BERT large. Oh, sorry. So these are the parameters. So OpenAI GPT and BERT base have the same number of trainable parameters. BERT large has way more than twice as many. BERT large is much bigger. BERT and OpenAI GPT are single model, single task. All results obtained from gluebenchmark.com/leaderboard. Bramati says, what's the difference between BERT base and BERT large? So it's these parameters. These parameters. So I believe L is the number of layers of attention modules in the encoder. So these guys, how many of these are stacked up in the encoder? So this thing that's labeled NX here in the original attention paper, and in BERT base it is 12, and in BERT large it's 24. H is, I believe, the number of hidden heads. I know I keep trying to figure out what it is because I use slightly different things. Then slightly different names than they do in the attention is all you need paper. So the number of self-attention heads that are trained at any given time within each of those layers, and then A is I straight up forget. Venkatesh says, can this model be used to identify book entry mentions in a given text? Possibly. So BERT is sort of a general purpose English language, very important model that the point is that you can fine tune it by changing the encoding for your input and then also how you interpret the output layer. So potentially you could use their named entity recognition architecture for that. It might be helpful. But I think it's only English, so if you were working with a language other than English, you'd probably need to retrain their sort of big BERT module. And I believe Ryan mentioned uploading the BERT model on Kaggle. Let me check that really quick. Yeah, so potentially. Oh, yeah, wait, what was A? I straight up forgot what A is. Yep. Nope. No, I want to know what it is. I want to know what the letter A actually means. Blah, blah, blah. Oh, sorry. The hidden size is H. The number of self-attention heads is A. So the thing that is called H here, I believe, is called A by them. Helpfully. Oh, she's a little bit slow today, huh? BERT. That's right. That's what I was looking for. User in datasets. Okay, yeah, it looks like a couple people have actually uploaded some pre-trained BERT models, so you could go and use those if you wanted to on Kaggle. Ryan says, the answer to life Wikipedia, what you do want to do is dig in more. DevSet is an additional set on top of that for validating results. And Shed says they mentioned results. The mentioned results were from here as well. So it's not just the leaderboard. It is also this blog post by OpenAI. So thanks for the link, Shed. All right, where were we talking? Scroll. Oh yeah, we were done with the boring parts where they were like, our numbers are bigger. It is interesting to observe that BERT large significantly outperforms BERT base across all tasks, even those with very little training data. The effective BERT model size is explored more thoroughly in section 5.2. All right, Squad version 1.1. The Stanford Question Answering Dataset, SQUAD, is a collection of 100K crowdsourced question-answer pairs. Given a question and a paragraph from Wikipedia containing the answer, the task is to predict the answer span in the paragraph. For example, input question: where do water droplets collide with ice crystals to form precipitation? Input paragraph: precipitation forms as smaller droplets coalesce via collision with other rain droplets or ice crystals within a cloud. Output answer: within a cloud. So reading this paragraph, if you were asked this question, the part of the paragraph that answers the question is within a cloud. The type of span prediction is quite different from the sequence classification tasks of Glue, but we are able to adapt BERT to run on Squad with a straightforward manner. Oh, I see. So they're not actually outputting answers. This is what I was confused by. So this is not something you would necessarily need to use you wouldn't necessarily need to use a decoder for this. It is just so given our question and our paragraph, where in the paragraph are the most important parts for answering the question. So this would be which tokens in the paragraph have highest attention when we train, with our reward being correctly highlighting the correct parts of the paragraph. Okay, so this makes more sense as an architecture given that. I wouldn't use it to answer questions. So if I gave you a question and was like, what's the answer? And your task was to predict the answer given the question, I probably wouldn't use just BERT. You probably would want an encoder and a decoder. Ryan says, basically learn from training set, try to optimize for validation set, use dev set in order to make sure these optimizations generalize, then use test in order to actually measure performance. Arnav says, you just need to point for the squad task. Yeah. Okay, that makes a lot more sense. Blah, 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 blah. We are able to adapt BERT to run on Squad in a straightforward manner. Just as with Glue, we represent the input question and paragraph as a single packed sequence, with the question using the A embedding and the paragraph using the B embedding. The only new parameters learned during fine-tuning are a start vector and end vector, S and E, where they're both vectors of real numbers of dimension H. Thank you for helping me with the math words earlier, guys. Let the final hidden vector from BERT for the ith input token be denoted as T sub I is a vector of length H of real numbers. See figure 3c for visualization. Then, the probability of word I being the start of the answer span is computed as a dot product between t sub I and s, followed by a softmax over all words in the paragraph, where s is the start vector. So p sub I equals e times the dot product of s sub e raised to the dot product of s and t sub I divided by the sum of e raised to the dot product of s to the t jth power for all values j, where j is the word in the vector, maybe? Where y'all getting j from? You just added a variable you never defined. Oh, this is my problem with math papers. The same formula is used for the end of the answer span, and the maximum scoring span is used as the prediction. The training objective is the log likelihood of the correct start and end positions. We train for 3 epochs or epochs with a learning rate of e negative 5 and a batch size of 32. At inference time, since the end prediction is not conditioned on the start, we add the constraint that the end must come after the start, but no other heuristics are used. Okay, so the finding the start vector and the end vector is, right, where, so the vector is sort of the, if we're looking at each token has a vector underneath it, and we are looking at each of those vectors. So the start vector and the end vector are specific tokens, and they just look for the thing that's probably the start vector, look for the thing that's probably the end vector, and then check to make sure that the end vector is after the start vector, and that's all they do. The tokenized labeled span is aligned back to the original untokenized input for evaluation. Tokenized labeled span is aligned back to the original untokenized. Okay, so they get the start and the end, and then they get all of the tokens between them, and then they sort of like match that to the original input to see if they got it correct. Results are presented in Table 2. Squad uses a highly rigorous testing procedure where the submitter must manually contact the squad organizers to run their system on a hidden test set, so we only submitted our best system for testing. The result shown in the table is the first and only test submission to squad. Also, I don't think that's what rigorous means. I think you just mean inconvenient. We note that the top results from the squad leaderboard do not have up-to-date public system descriptions available and are allowed to use any public data when training their systems. We therefore use a very modest data augmentation in our submitted system by jointly training on squad and trivia QA, Joshi et al. 2017. Our best performing system outperforms the top leaderboard systems by 1.5 F1 in ensembling and 1.3 F1 as a single system. In fact, our single BERT model outperforms the top ensemble system in terms of F1 score. If we fine-tune on only squad without trivia QA, we lose 0.1 to 0.4 F1 and still perform all existing systems by a wide margin. And then there's a table that's like, oh, look, we did better. We can go into it if you care, but I think that this is, again, the boring part of ML papers. Been Ready says, earlier you mentioned that transformers are not as good as RNNs, they won't capture complete architecture. Then how does BERT, a kind of transformer, perform better than RNN and LSTM? Oh, so what I'm saying is that they aren't as good at describing hierarchical structures in language. So that doesn't necessarily mean that they're not going to, so that's not with the architecture problem. It is more for things like parsing, or rather than sentence level entailment, phrase level entailment within a sentence, if that makes sense. So it's more of a fine-grained thing. And I mean, even if something is not theoretically as good, if you have more training time and more data, or if it trains more accurately so that you can do sort of more tuning over time, you might end up getting better results. And Arnav says, you can't really say which is better or worse. Transformers have been giving the better results recently. It should also be mentioned that BERT was trained for a lot longer than normal models. Yeah, they had a lot of power behind it. The Answer Life says, also BERT is trained on a lot more data in an unsupervised manner than used to transfer learning for fine-tuning. Yeah. Good discussion, guys. Thank you. Yeah, so it's hard to say, like, it's hard to make theoretical claims about specific model architectures and their qualities, and also that is not currently the goal of the research community, to my sometimes chagrin. Blah, 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 blah. All right, named entity recognition. So they did question answering and they did good. To evaluate performance on a token tagging task, we fine-tune BERT on the Connell 2003 named entity recognition dataset. This dataset consists of 200K training words which have been annotated as person, organization, location, miscellaneous, or other non-named entity. For fine-tuning, we feed the final hidden representation, T sub I, which is a vector of real numbers of dimension h, to each token I. I think for each token I into a classification layer over the NER label set. The predictions are not conditioned on the surrounding predictions, i.e. non-autoregressive and no CRF. To make this compatible with word piece tokenization, we feed each Connell tokenized input word into our word piece tokenizer and use the hidden state corresponding to the first subtoken as input to the classifier. For example, Okay, so they have the example, Jim Henson was a puppeteer. Oh no, this is a bad example. So Jim Henson is a name. It's JIM space HENSON. The word piece tokenizer is like, oh hey, son is sometimes an ending that's a morpheme on words, like, trying to come up with a good example. Grandson, and has split Henson into two words, two tokens, and they have assigned their the label from the Connell dataset to hen, which is, according to WordPiece, a single morpheme. And then, so the other example is puppeteer, which is two morphemes, puppet and ear, and they have assigned 0, so this is not a named entity, to puppet, and nothing to ear. So, in most cases, you don't want your tokenizers to consider words that are single names to be multiple tokens. So this actually I would consider an error and probably would not have used as an example in my paper. The answer to life says, ooh, that lemmatization. Yeah. So yeah, if I were to review this paper, if it were ever submitted to peer review, I would definitely call them out and be like, you guys, that, and definitely also the part where they're like, sometimes BERT large just collapses and we don't know why when you're training it. That's also something I'd be like, I'm gonna need a little bit more information right here. Where no prediction is made for X, so they don't predict a label for son or ear. Since the word piece tokenization boundaries are a known part of the input, this is done for both training and test. A visual representation is given in figure 3D. A cased word piece model is used for NER, whereas an uncased model is used for all other tasks. So they consider uppercase and lowercase words to be different tokens. So capital H, hen, is different from lowercase hen, is the example. Ryan says, the sentence piece tokenizer is bad, IMO. And the answer life says, busted BERT. I mean, I still think it's an interesting system, and I like their masking task, but, I mean, no paper and no piece of, like, literature is ever going to be perfect. There's always something that could be improved. But also, this has not gone through peer review, so I'm sure technical people have read it and given feedback on it, but that's not quite the same. Blah, 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 blah. So they used casing for word piece and for named entity recognition and not casing for everything else. This is only going to work in English and things like German, where all nouns are uppercase. It is not going to help you out. And in languages like Chinese, where there's no such thing as case, that is also not going to help you out. So this is a very English-centric word choice, a very English-centric choice. Results are presented in table 3. If I remember, they did better. Oh, look, they did better. BERT large outperforms the existing SOTA cross-view training with multitask learning by 0.2 on the task. Hyperparameters were selected using the dev set, and the reported dev and test scores are averaged over 5 random restarts with those hyperparameters. Wait, why are they averaged? Why are they averaged if sometimes they collapse? They said they did the random restarts and then picked the best system, didn't they? Am I making this up? We ran several random restarts and selected the model that performed best on the dev set. So this must be for glue specifically. So for glue, they picked the best model and submitted it, but for, where were we? NER, they averaged over them? That's an interesting choice. I would want more discussion of. Okay, so that's NER. SWAG, the Situations with Adversarial Generations dataset, contains 113 sentence pair completion examples that evaluate grounded common sense inference. Given a sentence from a video captioning dataset, the task is to decide among 4 choices the most plausible continuation. For example, a girl is going across a set of monkey bars. She jumps up across the monkey bars, struggles onto the bars to grab her head, gets to the end and stands on a wooden plank, jumps up and does a backflip. None of these are super plausible. A girl is going across a set of monkey bars. Maybe 3, she gets to the end and stands on a wooden plank. I guess you could jump up and do a backflip, but that seems like Xena level stuff. Okay, well, noted. The Answer Life says, isn't that just the test score for NER? Yes, so they only averaged over things for the NER. For glue, they always gave the best performing system. Picked the best performing system using the dev set. Adopting BERT to the SWAG dataset is similar to the adoption for glue. For each example, we construct 4 input sequences where each contain the concatenation of the given sentence, sentence A, and the possible continuation. The only task-specific parameters we introduce is a vector v, whose dot product with the final aggregate representation, c sub I, denotes a score for each choice I. Task-specific, so they add a new vector v that does what? Where is it from? Where is v coming in? We fine-tune the model for 3 epochs with a learning rate. Didn't they just do 5 e minus 5 and a batch size of 32 on the NER? Am I making that up? Did they talk about batch size in the NER? Oh no, it was in squad. Okay, is that like grid search? How'd you pick this? Why is it different for these 2 things? Presumably because it did better, but I don't know how they are picking those specific hyperparameters. Results are presented in table 4. BERT large outperforms the author's baseline system by 27.1. And they are also claiming to outperform single human annotators, but not consensus annotation. Human performance is measured with 100 samples, as reported in the SWAG paper. I'm confused by this task. Is it in here? Because I thought that they only had... Yeah, they don't have a little visual representation of the task-specific architecture that they added. So I'm not sure where they're... is it down here? No, I'm not entirely sure where this vector v is coming from. So I'm trying to find where I was in the paper. I'm not just like we introduce a vector, v, whose dot product with the final aggregate representation denotes a score for each choice I, the probability distribution of that. Okay. So the final aggregate representation is, so this is the final label, right? So the like label output from the first token that they're using as this CLS token. So I'm guessing they're taking the CLS token from each of the 4 representations, the final representation of the CLS token, so the C, and then taking this new vector, which is trained, question mark, dot product with the final aggregate representation denotes a score for each choice I. Yeah, so for each of the 4 possible inputs, so looking at each of the multiple choices, they take the dot product and do soft max. Is V trained? Or is it just like a vector of like where the correct one is 1 and the rest of them are 0? All right. I have no idea what's up with V. The Astral Life says, wait, why aren't they using a learning rate decay scheme? That's a good question, because they definitely talked about, and they might talk about this in the oblation. Oh no, so this is just for, so they used this paradigm of always using a batch size 2 and 3 epochs, and then picking one of the 4 learning rates only for the glue tasks. So I'm not entirely sure how they were picking learning rate for these other tasks. And I also don't know what their learning rate for the NER task or their batch size, because I don't think they mention it. Fine-tuning, representation, compatible, blah, 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 time, da, da, da. Yeah, they don't talk about either of those parameters for the named entity recognition task. Answer Life says, isn't V just the label? I think the label is the input to C, and then C is the final representation of that input. I think it would make sense if the V was the label, but they don't actually say that that's what it is. And it could be learned? I don't know. Okay, so definitely I feel like the glue results had the most discussion. I feel pretty happy also with the squad results, which also I believe used similar parameters to the glue results, and from there it just sort of gets a little bit weirder. I don't know, these last tasks feel like a little bit tacked on, because they're anyway, interesting. So we're gonna come back next week and talk about ablation studies. So this is basically they're doing more experimentation with the model itself and seeing what the effect is on the final output. Yeah, I'm curious to read this and find out a little bit more. I think they got good performance. Like I almost knocked over my cup. The empirical results are definitely, very exciting. But yeah, I definitely want more details, or also maybe like 2 fewer tasks and just more description of the tasks that the other tasks. So a little bit more in depth about what they did. But I think also all their code is available online. So let's see. BERT GitHub. Yeah, so their TensorFlow code is available online. It looks like at least somebody has translated it into The PyTorch is the other framework I was trying to think of. And it looks like they're also doing some multilingual modeling, which is definitely exciting. There would be some changes that they would need to make to the choices that they made, especially for named entity recognition, if they used a language like Thai or Mongolian, which is going to have a fairly different set of orthographic rules. But anyway, I got other stuff to do. Danielle says figure 4 might be revealing. Okay, we'll save that for next time. Little treat to look forward to. And Ryan says Christoph made a Keras version that's much easier. Oh, that's helpful. Which he linked. I personally generally prefer Keras to TensorFlow. I think it's just more user friendly. And at one point I had a pretty okay mental model of what TensorFlow model specification was doing, but there's like some weird caveats and stuff, and I've definitely lost all of that since I haven't been practicing it. So, all right, so I'm gonna wrap it up today there. Thanks very much for joining me, and I think I might actually take a break from the Transformers project on Friday, because there's a co-entity, a co-reference resolution competition that just launched, and maybe I'm gonna spend a little bit of time getting started in there. Just writing a little bit of a starter kernel. I do want to get back to the Transformer stuff because I want to figure out why it's not working and then make it work. But at this point I have, a certain amount of frustration with the project, and it's going to take some time to dig into it. So I might do something a little bit of a detour and then come back to it. Ryan says that competition already broke. No, very sad. I might still play around with it anyway. Okay, so I'm going to wrap it up for today, and I will see you on Friday at 4 p.m. Pacific, or next Wednesday. And I'll talk to you guys then. Thanks for joining me today. Have a great rest of your day or rest of your night, wherever you are in the world, and I will see you later. Bye.